So the end of the last segment, we got to this point. We were adding 4 vectors together here, and we want to get back home. So this vector D is what we're going to be looking for. This is vector D. And we want it to equal right back home, which was at the pole, at 0x and 0y. Okay, so do the math. Vector D then is going to be equal to, if you move these vectors A, B, and C to the other side of your equation, you're going to have the opposite of each of these, aren't you? Minus A, minus B, minus C. This is vector algebra. The original problem that we're posing here is called an equilibrium solution. Equilibrium solution. Because what we're doing is saying a sum of vectors is equal to 0. A 0 or a null vector. Sometimes we call this a null vector, where the components are 0 in value. And so the sum of the vectors equals 0. Oftentimes we call that an equilibrium solution. Okay? So the way we're going to set this up for vector D then is we're simply going to factor and assign a negative to the whole mess. Now look at this mess I'm going to draw. Don't forget this negative right here. I'll probably circle it. And what I'm going to lay in here is (30) cosine of the standard angle, 130 degrees, comma, 30 sine 130 degrees. And we're going to, inside there, add to it 15 cosine of 300 degrees, comma, 15 sine 300 degrees. And lastly, 12 meters cosine of its standard angle, 190 degrees, comma, 12 sine 190 degrees. This is not the only way to do the math. There's a multitude of ways that you can take to get the answer. I'm just showing you what I found to be the cleanest, simplest way to do it. And then what are you going to do to find your answers? As we did in the last session, we're going to just add up these x components, aren't we? Together. We're going to add these guys together right here to end up with our final component, x component of D. And don't forget, we'll assign a negative to the result. And then similarly here, we're going to then add these y components together. And I can use the memory of the calculator to do that pretty efficiently. So, over on the calculator now, checking the mode of the calculator, I'm in degree mode. And so here we go. 30 cos 130 plus 15 cos 300. And I'm adding to it 12 cos 190. And should I store that somewhere? Where should I store it? Store alpha x. Sound reasonable? Okay. Now, do I want that negative 23.6 meters? What do I want? I want to change the sign of it, right? Because of the negative that was originally in the problem there out in front. So I'm going to change the sign of that. So I'm going to take the negative of that answer and I'm going to store it back in x again. Now, okay, right? And then finally, I'm going to then replay the previous expression. I just go back twice there, and I just come back up here and change this to sine. It's real easy to edit this with your calculator. Whoops, if I didn't screw it up. Sine, thank you. And I'm going to store it in cell y, alpha y. Okay? And then I got to change the sign of it too, don't I? Okay. I'll just do it the way I did previously. So I'm then going to take the negative of that answer, and I'm going to store it back into y again. Okay, so I have these answers sitting on my screen right there. So then what I can do is I can come down here and observe that the d vector, the equilibrium vector we needed to get back home, is equal to a positive, this is a dx term and a dy term, which happen to be 23.6, comma, negative 7.9 meters. Always put your units on your result. So there it is. Let's draw a sketch. Remember how we catch mistakes by drawing sketches, okay? So let's draw a sketch of this thing, and I'm going to go ahead and come up here and draw this now and try to make it somewhat to scale. So my first one was 30 at 130 degrees. That's our longest one, I believe. Okay, so there's the 30 at the 130. And then from there, now, here's my compass. I'm now going to go on my second vector at 15. Let's see, that angle's 130, which means this is 40. So that means this angle right in here is 40. So I want to travel at 30, don't I? A distance of half that. Right about here. And that standard angle on that vector was 300 degrees. Right there. There's your 12. And then finally, and our 15 was here. Oh, I'm sorry, our 30 was here. 30 and 12. Oh, damn, sorry. 15. 30 and 15. And then what was our third one? 12. And what was our angle? There it is. 190 degrees. So our compass is here. 190 is going out this way, isn't it? A distance of 12. Okay. Where is D on this weird looking picture? Where is D? It goes from here, doesn't it? Because remember, A, B, C, D added together gets us back to the origin. So our vector, our final vector D is this thing. There's D right there, going back up that way. And the distances were, boy, that seems strange.
You went to it with 30 meters. The origin should be by the 130 degrees.
Yeah.
Oh.
Right there.
Oh, yeah. Oh, man. Why was I going up here? Wow. I'm really lost.
Drop something over there.
I'm out in the rain. Okay, this is correct. 30, 15, 12. Ah, now I'm feeling much better. Good. Thank you. I'm sure glad we have a class here because I catch my mistakes. So we're going from here back to the origin. As a matter of fact, it'd be a good idea to make a big note. There's your origin. So here's D, folks. And notice what we had for D. We had 23.6, comma, minus 7.9, approximately, for your D vector. And that looks about right, doesn't it? It looks about right. And then the length of that, what's the magnitude of it? 23.6 squared plus 7.9 squared, square rooted, right? And you can just take your x squared plus y squared and square root that and pick up your result. And you get what? Do it real quickly here as well. Square root of x squared plus alpha y squared. And store it in memory cell D. Hold it. I had an extra zero sitting in the front here.
Sure.
24.9. So D is about 24.9 meters. To get you back home to the starting point, 24.9 here, to get you back home. And then what's the heading? I usually would suggest you draw a picture and we want that vector's heading. So you're going to go what to find the angle here? Aren't you going to go inverse tangent?
Yeah.
Yeah. So theta is going to be your inverse tangent of your y reading over your x reading, dy over dx. So we're going to go inverse tangent of alpha y divided by alpha x, and I'll store that in memory cell alpha theta, minus 18.5 degrees. I mentioned the other day, what has to go along with this? Your brain. Is that pointing in the correct direction? Is this pointing in the correct direction, folks? Standard angle minus 18.5. Does it look right? Into the fourth quadrant. Okay? You have to use your brain to double check this to make sure this, there's only one answer that comes out from your inverse functions. Only one answer. And you have a second quadrant answer or this thing that might show up potentially. So you always have to think about what your x and y readings are here as to which quadrant this thing is really pointing into. And so this will get you back home then if you travel this distance at that angle. All right. So that is not quite finished this. I want to do one more real quick thing. I've got about 2 minutes and I can do it real quickly with you because what we've been doing is distances. It would be really useful for you to have a little bit of exposure to an equilibrium problem with forces. And it'll only take a second to do this. Force equilibrium. Force equilibrium. So let's say I pull on a rope with, say, 50 pounds at 10 degrees here. And I pull with another rope over here at, say, 70 pounds. And it's at, say, 30 degrees from here. And then I have a weight that I want to apply straight downward, so that this thing won't take off and go anywhere. Doesn't that make sense? I need a certain amount of weight here if I had these two forces pulling like that, like tug of war. We hook 3 ropes together. Wouldn't we need, if I wanted a weight pulling exactly in that direction at 270 degrees, wouldn't I need a certain weight pointing straight down there? Okay. Is there any x part of this weight? No. Is there some y part? And it's the whole magnitude, isn't it? Right? There's no x part on this because it's pointing straight down. And all of the weight has to be pointing straight down. So it has to be some w value. Okay. So all we have to do is go ahead and write this equation for the sum of these 3 vectors. So watch. I'm just going to write it down here because I don't have time to actually finish it. I'm going to just write it down, then you can punch it. Watch the way I do this. 50 cosine of 170 degrees, and the y part of that is 50 sine 170 degrees. and I'm adding to it 70 cosine of 30 degrees, 70 sine of 30 degrees, and I'm adding to that what I need for equilibrium. I could say W cosine 270, W sine 270 there, or I could just do this. And that mess must equal, the addition of these must equal 0x, 0y. You can punch that out, figure out that problem. Hold it. You know something? That's not going to work. These are not going to equal 0. Because this is a leftward part of force, right, and a rightward part of force. They'd have to be equal, wouldn't they? So there is something that's skewed off here, so this isn't going to be directly downward, folks. So it's going to be at some direction like this, right? Let's call it a vector E. And so there's going to be something hanging right here, E cosine some theta and E sine some theta, and that mess must equal 0 as a vector.
How would you determine that angle?
There are two unknowns in this equation, aren't there? You write this equation for x stuff with two unknowns, you write that equation for y stuff with two unknowns, and by substitution you can solve for E and theta. So we're so excited that in the next session at the very beginning we'll finish this. And then we'll start on parametrics. So I'm sorry I didn't get to parametrics today.